Hello friends, in today's video I'm going to discuss about heat engines. So heat engine is a cyclic device by which heat is converted into mechanical work. Excuse me for my handwriting, please. First we will be dealing with heat engines, and then ultimately we will be moving to Carnot's heat engine. Now, as I said, your heat engine is a device by which you can convert heat to mechanical work. The main part of an heat engine is a reservoir at some temperature T1. Let me draw that reservoir T1. It acts as a source of heat. You have a working substance here, and then you have a sink at some lower temperature T2. T2 is less than your T1. Now this working substance extracts Q1 amount of heat from the source, does W amount of work, and rejects Q2 amount of heat to the sink. So using this diagram, you can very well understand. I can write this equation: T1 plus W is equal to T2. Sorry, I wrote it wrong. We can write Q1 plus W is equal to Q2. So W is my expression right? No, I cannot write this. My total amount of heat energy is Q1, out of which W is the amount of work, so I am left with Q2. So yes, this is my correct equation. So W is Q1 minus Q2. Using this, I can write the expression for efficiency. It is the energy output by the energy input. Q1 minus Q2 by Q1, which is 1 minus Q2 by Q1. And if you want to calculate the percentage of efficiency, you can write like this. You can multiply with 100%. As you can very well see, the efficiency is never going to be 100% here, because you have one minus factor here. It can only be 100% only if your Q2 is going to be 0. Then you will have the efficiency 100%, but this is never possible in reality. So now let's move to Carnot's heat engine. Let me first discuss about the main parts of a Carnot's heat engine. You have a working substance. This is the container in which I am keeping the working substance. The bottom part of the container is a conductor. It's a conducting base, but the rest parts are insulation. They are insulated, means there cannot be any heat exchange. And your working substance is here. You have a piston here, and then you have the weights. If you want to expand your gas, the working substance is gas, say. If you want to expand it, you can lift up some weights. If you want to contract it, you can add some more weights. So in this cylinder, I have kept my working substance. Next, I have a source at some temperature T1. Now here for the source, let me draw it properly. See, in this container I'm going to keep my source. The top part is conductor, but the rest three parts I'm insulating, so that there can be no heat exchange from these three sides, the shaded sides. This is my source at some temperature T1. Then I have another part which I am calling as heat insulation stand. It is insulated from all sides. I don't want any heat exchange from any of the sides. This is heat insulating stand, and then I have my sink similar to source. After all, it is also reservoir, but it is at lower temperature. So what am I going to do here is, in this parts of Carnot's heat engine, I'm going to make some process. I'm going to make this working substance undergo some process, which I will plot in my PV graph, pressure versus volume graph. The first what I am going to do is, I will take my working substance, I'll take the cylinder and I will put it on source. As you can see, the conductor, the bottom part of this working substance and the top part of the source is the conductor, so there is going to be heat exchange. I'm going to keep the cylinder on the source and I'm going to lift up some weights so that there is expansion, and I am making sure to do it very slowly so that I can say that the process is an isothermal process and it takes place at temperature T1. And then I am going to plot it. So if I plot it, I am getting a curve like this. Say the initial volume was VA, it is expanding to some volume VB. Let me name this point as A and let me name this point as B. Now I will lift this working substance from the source, and now I'm going to place it on the sink, and again I'm going to remove some weights so that there is expansion of the working substance. But now, as you can see, as I'm keeping it on this heat insulating stand, there is not going to be any heat exchange. So this will be an adiabatic process. So an adiabatic process in a PV graph looks like this. So this point is C, and here the volume has increased to Vc. Now again, I will lift my cylinder from this heat insulation stand and I will place it on the sink at temperature T2. And now what I am doing is, I will add some weights. I'll add few more weights so that there is contraction, isothermal contraction. I'll make sure that the process is taking place very slowly so that I can say that it is an isothermal contraction. Say the volume has now reduced from some value Vc to some value Vd here. And then again I will place my cylinder, I will lift it from the sink and again I'll place it on this heat insulation stand, and again I will add few more weights so that I can say that there is contraction, adiabatic contraction. And my graph will look like this. It goes back to the same point. So this was an isotherm, say at temperature T1, and this isotherm is at, say, at temperature T2. T1 is the temperature of the source and T2 is the temperature of the sink. So point A, the pressure value is PA and the volume value is VA. At point B, say the pressure value is PB, volume is VB. Here it is PC, VC, and here it is PD, VD. Now during this expansion, isothermal expansion, Q1 amount of heat was absorbed by the source, sorry, not by the source, Q1